right, this mini lecture is going to be really brief about a concept that we hear, a perception that we get in sound known as beats. So if you've ever been listening perhaps to a band warming up and you have to, or if you were yourself an instrument player when you were tuning your instrument, you hear music coming from, or tones, pure sounds, pure frequencies coming from an instrument. Two different instruments may be close by each other, and instead of hearing this nice, beautiful tone, you hear this sort of wah, 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 wah kind of a sound. The sound itself isn't being generated by those instruments, but you're hearing this sound with a periodicity that in and of itself sounds like a wave, this wah, wah, wah sound. Or if you're tuning your instrument, if you are a musician tuning your instrument, and the primary clarinetist, principal clarinetist, or principal violinist plays a perfect tune that you're trying to tune to, you play your note listening for that wah, 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 and adjust your instrument until that wah-wahing goes away. Well, that noise that you hear, that you hear is what we refer to as a beat. Okay, so the frequency we call the beat frequency is what you hear when two sounds are interfering with one another. And we hear these best when they're very close. We can make out the beat frequency often when they're very close. So when two pure sounds are interfering with each other. And I'm going to do my best to hold steady. I'm not going to attempt to draw this. I'm going to hold this image from a textbook very steady, trying to give you a sense of what this beat frequency comes from. We already have the information. You've already used this information when you looked at superposition, interference, right? Interference, superposition. Interference is the act that's happening. Superposition is how we calculate it. So you can see in this top one, I hope you can see that well. I'm trying super hard to hold it steady. We can see in this top line that we have a frequency. The lower line is a very similar frequency. So two waves that are being generated, and then they're interfering with one another. And where they have destructive interference, the resultant wave is very low amplitude, and where they have constructive interference, the resultant wave, of course, has a higher amplitude. And if we sort of squint at this superposition of these two waves, we see that it itself appears to have some wave-like behavior. And I'm not sure you're going to see this one as well, but if we draw a little envelope around that wave-like behavior, we see a wave with a certain dimension, wavelength, if you will, and of course then it has a certain frequency. That frequency of that envelope is what's known as the beat frequency. So this is the envelope of the interference, of the superposition. I'll use that word instead because that's how we describe the resultant wave when we learned about how waves interfere and act with each other. So the envelope of that superposition is what the frequency of that envelope is what we refer to as the beat frequency. So where does it come from? It's actually beautifully simple. I love when physics is so beautifully simple. The beat frequency is simply the difference between the two frequencies. That's it. Mathematical subtraction, the difference between the two frequencies. Now, I put absolute values on there because there's not really, it's a scalar quantity. There's no such thing as a negative frequency or a positive frequency. So if I define the higher frequency as frequency 1 and the lower frequency as frequency 2, great, then I get that positive number. If I'm talking about two objects and I define two sounds or instruments, I'm defining one as 1 and one as 2, and 2 happens to be the higher frequency, great, then I get a negative number and I take the absolute value. So the important piece is the beat frequency is simply the difference between the two frequencies. So if you are tuning to a frequency of 440 hertz, and you hear a beat, a wah, 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 and you're sort of counting out that wah-wahing, as great musicians too. If you hear a beat of 2 hertz, what does that tell you should do? Should you make your instrument a little bit lower, or should you make your instrument a little bit higher? Well, if all I know is that there's a beat of 2 hertz, that could mean I am playing at 442 hertz, or I'm playing at 380 hertz. How do I know which one? Well, I test it, right? So if I make my instrument a little bit longer, I pull out my tuning slide, then I'm increasing the length, increasing the wavelength, decreasing the frequency, and my wah-wahing gets a little bit better. Well, then I was a little high, and I can adjust until that beat goes away. If I'm a little bit low, I adjust until that beat goes away. And so we can use beat frequency to tune our instrument. All right, so very straightforward relationship, recognizing that this is all just about interference and superposition, and then kind of defining that envelope of that is the beat that we're talking about. We hear it because we're hearing this periodic wave coming through. That is the superposition of these other 2 waves. It's sort of like on top of the waves that are hitting our ears, and it's simply the difference between those frequencies. Good job.